In the last capsule on electronegativity, we'll first review what we did in electronegativity 2 and then move on to two more examples. So electronegativity stabilizes anions and have seen these examples here. The first example we saw was this one. Fluoride ion is more stable than hydroxide, which is more stable than amide, which is more stable than the methyl ion. And we ascribe that stability to the electronegativity of the atom. So since fluorine is the most electronegative atom, it can tolerate, it can accommodate that extra electron which confers the negative charge on it. Oxygen is less electronegative than fluorine, so it can still stabilize it, but not as much as fluorine. So hydroxide is less stable than fluoride. Okay, so now in this one here, fluoride is most stable ion of the four there. Okay, fluoride is the most stable ion. In what we are saying by saying this, just let me put a different spin on it. Fluoride is most stable ion. In other words, in terms of reactivity, yes, we do many organic reactions. In terms of reactivity, that means whatever is most stable is least reactive. Skip that. We come back to that every now and then. Whatever is stable will not react. Like noble gases. Noble gases are stable in their full octet, so they don't react. So same thing. If something is stable, it will not be very reactive. So in this series of ions, fluoride is the most stable and methyl is the most reactive. Okay? So keep that in mind. Most stable means least reactive. Least stable means most reactive. Okay? So we have seen that, and I added this stability and reactivity equation here. Most stable, less reactive. Less stable, more reactive. Okay? Now, another example we have seen in the previous video, electronegativity 2, is this order here, and in this one, the negative charge is on oxygen atom in all cases. But we are still able to predict the stabilities of these ions, these four ions in this order, because fluorine here is more electronegative than chlorine, which is more electronegative than bromine, which is more electronegative than the hydrogen there. So fluorine is able to pull the electron density away from the oxygen much more than chlorine, which does more than bromine, which does more than hydrogen. And we also came up with a nomenclature for that. What do we call this effect? This effect is called negative inductive effect, or minus I. Now, with that review, we'll move into two more examples of electronegativity and stability, and then we'll go to a different topic. Okay, so the other example that we want to see is, let's draw four compounds: CH3O-, CH2O-, and let me put a fluorine there. And now what I'm going to do, I'm going to add more carbons. Okay, so there's that, and one more. Now, okay, just complicating matters, we can include methoxide. Methoxide, I've just called methoxide, this is methoxide. But we have these four ions now. Again, what do we see? the negative charge is on the oxygen atom. So the electronegativity of oxygen, whatever it is, it's constant in all cases. But what's different in these four ions is fluorine. I mean, if you want to differentiate, want to attack the problem, you can break this problem into two parts. One part is like that. One of the compounds or ions has no fluorine. The other three compounds or ions have fluorine. So one way to differentiate between them. Okay. So we differentiated, one part, second part. Now let's see this part. This part, there's fluorines everywhere in every ion. But what's different? It is the distance. How far the fluorine is from the oxygen. Of course, fluorine is most electronegative element. Okay. But the distance from the oxygen also matters. So yeah, fluorine is more electronegative. But the farther it is from the negative charge, the less effect it will, the less minus I effect it can exert. What's minus I? Inductive effect, inducing the electrons away from the oxygen. In this example, oxygen. So fluorine is, close by. There's only one carbon between the oxygen and fluorine, so it will have its greatest effect there in these compounds. And in this, I'll just number them compound ion 1, ion 2, ion 3, ion 4. In ion 2, fluorine is closest to the oxygen and the negative charge, so it will have the most minus I effect. In the compound ion 3, fluorine is 2 carbons away, so its effect will be reduced. And in ion 4, the fluorine atom is 3 carbons away, the effect still falls off. So the minus I effect tapers off as the distance increases from the negative charge. Okay. So based on that, how can we, let's arrange these four ions from most stable to least stable. 2 is the ion, most stable ion. So 2 is more stable than 3, which is more stable than 4, and then comes 1, just 3 hydrogens. So no fluorine atom. So this way we solve this problem. Okay. So we can, there are ways to, experimental ways, or maybe you can find some data online. We have not talked about acidity yet, but we can talk about acidity and pKa's, and we can go into literature and check whether this prediction is true or not. But we don't want to do that here. We make a prediction, and many multiple choice questions on exams will be like this. So this is about utilizing electronegativity to explain things. So that's what we need to learn. We learn some concept and then apply that concept to solve problems. Now, this is it. We'll go to another example now. So I'll erase this. So in another example, we'll have the fluorine atom on the same carbon, but we'll keep adding more fluorines. Okay. I will take this particular ion as our base scenario, CH3, C double bond O minus. This is called the acetate ion, and this ion comes from acetic acid, which is dilute acetic acid, really dilute, the water we use in pickles and things like that is vinegar. Okay. This is acetic acid. we take the corresponding, the ion derived from acetic acid as our starting ion here, and then let's say I'm going to put CH2 COO minus, but I'll put a fluorine there, and now I will put two fluorines, and then another example compound or ion is this. So again, let's label this 4 ions just so it's easier to talk about them. So ion 1, ion 2, ion 3, ion 4. Okay. So here again the negative charge is on the oxygen atom. Okay. So looking at oxygen atom will not help us make any predictions about the stability of these ions, but then we move away from the oxygen, look at the structure of the ion and see what are the differences. The differences is, this is our, let's say this is our base unit, there's 3 hydrogens and carbon and the C double bond O, single bond O minus and all that. And then you see one fluorine atom, and we have already seen fluorine atom will have the minus I effect. So it's able to induce these electrons away from oxygen, so thereby stabilizing that negative charge. The oxygen electrons are spread out over the whole molecule, because of this fluorine is pulling them away, which stabilizes that. The negative charge is not localized, it's not in a hurry to react. Now, so one fluorine atom is able to do that. In ion 3, you have 2 fluorine atoms, so 2 fluorine atoms are much more powerful than 1 fluorine atom, so there is some additive effects coming up here. 2 fluorine atoms will be able to pull the electrons away much more than a single fluorine atom, and in this ion you have 3 fluorines, so the effect is even more pronounced. So with that, ion 4 will be the most stable, followed by ion 3, followed by ion 2, followed by ion 1. So this is the answer to this problem here. Now, good. So with this, we finish our electronegativity, and I want to bring in another topic here that comes from what we covered in a few videos before. It comes in loose dot structures, the concept called resonance. So let me bring resonance back here. We introduced resonance in, I think, loose dot structures 3 or 4, I don't remember now. But what's resonance? Resonance is again delocalization of electrons. So I'll compare now. Why did I bring that here? So you see this negative charge here on this oxygen can be delocalized like this. So resonance is shown by 2 arrows. So, and then you have the newly negative charge there for this one. So this is again delocalization of electrons. At one time electrons are on this oxygen, at another time electrons are on this oxygen. But if we call it oxygen 1, oxygen 2, oxygen 1, oxygen 2. So you see the negative charge is not localized on oxygen 2. Sometimes it's on oxygen 1, which confers stability again. So it's an interesting thing here. So for that reason, acetate ion, this ion, for example, is more stable than, let me give you another ion here. So that ion. See, this ion, CH3O minus, is less stable that means more reactive. Less stable means more reactive. Less stable means more reactive. And so in this cases, so we are comparing two compounds here, right? Two ions, CH3 C double bond O versus CH3O minus. In both cases, the negative charge is on the oxygen atom, right? In both cases, the negative charge is on the oxygen atom. So how are we saying, or why are we saying that the acetate ion is more stable? Because the acetate ion has resonance, and we have shown that here. Okay, so there are multiple ways in which a negative charge can be stabilized. We focused on electronegativity in a couple of videos, and towards the end of this video, we're just bringing in another topic which we just briefly introduced in reduced order structures. Okay, resonance. So we'll talk more about resonance. We'll make maybe 3-4 videos on resonance, look at various rules of resonance. Okay, so we stop here.